Okay, so assignment 3. It's been out for a week and it's due in 13 days. Monday of week 10. Yes. Assignment 3 is. Assignment 1's a very old assignment. It was written years and years and years ago. We've just adapted it. Assignment 2 was written by Brad Heap, and we've adapted that, and that one was written by another one. Assignment 3 is another one that was adapted in 2019, I think, where we wanted to do something more complicated than, just like a vector or something. So we made a graph assignment because we wanted to get students comfortable with, in particular, templates and custom iterators, like the week 7 topics. That's like the bulk of what this assignment's about. So it was really about, can they get comfortable with templates and custom iterators? But it was also designed to be quite just a bit more complicated to actually really hone in some of your C++ knowledge. So the good thing about this assignment is that, structurally speaking, in assignment 2, and I know many of you who haven't started this will have started this or are like, yeah. But in assignment 2, we asked you to create a Euclidean vector, which was basically an object that could store values as like an array. It was like an array wrapper, but for a vector. And yeah, that was the gist of it. And we asked you to use operator overloading and some smart point, not really much with smart pointers, but a little bit with smart pointers to basically define your own library and avoid using STL containers, but instead, use primitive style arrays. We gave you a bunch of member functions and constructors and this and that to implement. In assignment 3, though, we're expecting you to do a similar thing, except instead of making a Euclidean vector, we're asking you to create a graph, a generic graph. So that's a graph whereby the type of the nodes here, type T here, and the type of the edge weights here, U, are generic. They can be any type, in particular ordered type, I think. But, we just test this with strings, ints, doubles. Like, it's not rocket science. Like, we don't test it with crazy things. It's just strings, ints, doubles, chars, like, stuff like that. So you can have a graph of kind of any type you want. Like assignment 2, the graph is defined in graph.hpp, and because it's gonna be a templated type, you have to put all of the definitions inside the HPP file, either inside the class body or underneath the class body, depending on your judgment as to whether you think it's sufficient, like whether it's the right thing to do. So very similar. It's a class. This one's going to be templated. We haven't put the templates here. Anyone who started has probably put the templates there themselves. In fact, like, it really depends on how you want to go about this. Some of you might prefer to go about this making the entire graph work just for like ints of ints, and then go back and template everything. I don't know if I would necessarily recommend that. I know it's something that some people would find easier, and if that's really your jam, then go for it. The main reason I say that is because it's probably very easy to underestimate how painful it would be to retroactively put template type name in all the right spots, and you'll come across a whole bunch of errors. So if you do take that approach, my only advice is don't think you'll just like in an evening go and make it templated or whatever. But I would recommend you start off actually making it templated. The cool thing about the graph is that it's going to follow a really similar structure to the books and the rope examples from lectures. So in my tute today, in tute 8, which will get uploaded tonight, we did an example of this, so you can go watch that, or go to your tutor's tute, go to whatever tute, it doesn't really matter. Maybe it's not here. Is it here? Class temp instack. Oh yeah, we did the instack example. So it's like, if you're looking for inspiration for the custom iterator part, you can go look at the instack example, or you can go look at the tute 8 examples that we went through, because your graph will follow the same general pattern of, you've got a class and it's got a class iterator inside of it, and then you've got some begins and ends, and like you can look at stuff like this, or the tute 8 rope example, to really get yourself like a bit of a bedrock in how this works. In a general sense, there'll be some extra little things you have to consider. Probably one of the more let's go into it as we go, but um, this is your templated graph. Generic directed weighted graph is the namespace it's in. You have a graph, it takes in two templated types. Because it's directed, there is a sense of order with your edges. So if something has an edge from A to B with weight E, that doesn't mean that there's an edge from B to A. So edges, edges are directed. Sorry, I'm just reading some of this again. Dimitri says, can we take instack as an example? I think instack is a great, I think instack is a good example. It's not perfect. Instack is not templated, number one. Okay, that's a really important thing. Like your assignment expects you to do a templated type. Instack is bidirectional. No, it's not. Sorry, it's just const. Is it? No. So I think the only two things are that one is that instack is a forward iterator. The iterator you want for your assignment is bidirectional. That's one particular challenge. The other thing is that instack is not templated, which is kind of relevant. We've been very kind to you, and we've actually given you the full iterator class definition. So you can actually copy and paste this in. You can copy the whole thing in. Most of it's all the declarations are done for you, which is great. We've made it clear that you have to define the equals operator, the post and pre-increment in both directions, the pre-increment, post-increment, pre-decrement, post-decrement, the dereference, the constructor, and then just the iterator traits here. Most of these are defined for you. And in fact, value type or graph NE value type is already kind of defined for you too in the .h, in terms of we've actually defined it here. So as part of the graph's public, in the public part of the class graph definition, there's actually a struct value type here. And when we designed this assignment, there was a lot of debate as to what iterating through it means, because it's how do you iterate through a graph? That's a bit weird. Most data structures you can iterate through pretty intuitively, but what we decided was that iterating through a graph is iterating through its edges in sorted order. I think it's still sorted order. In some kind of sorted order. But that sorted order is based on first the source node, then the destination node, then the edge weight. So if you have a whole bunch of nodes and stuff, it's each time you iterate through the graph, you will get a little struct of three values, n, and e. So the from node, the to node, and the weight node. And the point is that they should all be sorted in terms of the from node first. So it's if you had a graph like this, 1, 2, 3, 4. The point is that fuck it. Let me just draw something slightly different really quick. If I had a graph like this where I had 1, 2, 3. There's 1. I'll draw some arrows. I'll give these letters. There's 1, there's 2, there's 3. This is A, this is B, and then this is C. It's if you were to try and iterate through that, you would get 1, 2, B, 1, 3, A, 3, 1, C, like that. So you'd get it in order of it's always sorted by the from node, then it's sorted by the to node, then it's sorted by the edge weight if there were multiples. I think an important note to point out is that up the top of this, it's made clear that edges can be reflexive. That is to say, the source and destination nodes of an edge could be the same. That means that you can have edges point to themselves. And then also, G is a multi-edged graph, as there may be two edges from the same source node to the same destination node. So it's possible that you then have another directed line here of weight D. So the source and the end node can be the exact same as well. But that's the graph structure. So you have to store that graph structure generically and make it iterable. And in fact, half the assignment's just making the graph structure and the operations of it. The other half is probably getting the iterator working. I don't even want to say that's half, because I don't think it's half. But as you can see, there's constructors. There's a default constructor. There's an initializer list that takes in a bunch of nodes, as you can see there, initialize a list of n. There's a iterator that takes in an iterator of nodes. Move constructor. Apparently there's no copy constructor. Move assignment. Oh, sorry, we just organized them the wrong way. Copy constructor, copy assignment. They're all the kinds of ways of creating it. Then we have the modifiers. You can insert a node, insert an edge, replace a node, merge, replace a node. This was a little drawing that a student in 2019 made. They were like, "Hey, is this what you mean?" And we were like, "Yes, that's a really nice way of describing it." So we just put it in the spec. So I can't remember who made this. I wish I had put a credit there. That's really lazy of me. I mean, they were happy about it. They're not like mad. It's just I hate forgetting who that was because that was really useful. So merge replace node is quite well specified there. Erasing a node, erasing an edge based on an iterator instead of a value. Pretty standard stuff. Clearing the graph removes all the nodes from it. We've had questions in the forum already about, can this be... can we use STL containers? Yes, you can. We're not expecting you to use primitive arrays. Lots more functions. And then you get into the iterator access, the begins and the ends. Begins for const objects, the begins for end objects. I don't know if we made this editable. I can't remember. I mean, it'd be written here somewhere, so I won't comment on it. But, operator equals output operator, blah, blah, blah. There's just stuff to do. So, and it's a lot like assignment 2. It's just harder, right? Which is the cool part. So, you get it, right? If you get assignment 2, you get this assignment, then you just have to make sense of templates and custom iterators, and you're done. You just got to do the work. So, do the work. We have another iterator. Well, not another iterator. Sorry, I'm really tired. This is our iterator definition again. Because you can copy and paste this, we hope that it takes some of the stress away for you in terms of worrying about what this is. I haven't looked at the spec for a few weeks because I kind of polished it up and then just haven't looked at it since we released it because last week was just a horrible week. In terms of the iterator, there's more specification about how they work. We gave examples about what a sorted graph means, so you can actually look at an example here. The only thing missing from this example is 2 edges that have the same source and destination node, but you can I trust you all to make sense of that. Blah, blah, and then we have our compulsory internal representation. So this is the only thing worth making note of. So we don't tell you how to store your nodes and edges. You can use vectors or sets or anything you want. The only things we specify are that they have to be heap memory stored. So whatever structure you use, the actual nodes and edges themselves are heap objects, right? And you can see this here by... So what we expect is that if you create a graph, I think this one's important. If you create a graph and then inside a scope you create a string and then you insert that node into the graph, while that string is copied into the graph, you need to create your own copy of it on the heap, such that, if whoever kind of gave you that value at the start, if they disappeared or they went out of scope, you still hold that value validly, right? And the resources of your graph should outlive the caller's resource. So once it gets into your graph, it outlives whoever gave it to you until you're done. So we do expect you to create memory on the heap. You do need to use smart pointers for that to solve that problem. So someone gives you a stack string, you use a smart pointer and to create a heap object managed by that smart pointer of that node or whatever. The constraints to point out are that for each node in the graph, you're only allowed to have one underlying resource stored in your graph for it. Now, this is, I guess, important depending on what your implementation is. Basically, in your representation, you might have pointers to nodes. You might have multiple pointers to the same node, depending on how you store things. For instance, if your graph is just here's a simple example, right? You could have a standard vector of n. There's all your nodes. And then you could have a standard vector of the value type, right? Something like this. So therefore, like, and this is your like array of edges where like each thing is like, you know, node 1, edge A, node 1, node 2, edge A, node 1, node 3, edge B, like whatever it is. The thing is though that in this particular structure, you have this 1 used a few times, right? And the point is that if you have any kind of data structure that references a node multiple times, you need to make sure that you're not duplicating that. As in, these three things these should all be pointers to the same kind of like one underlying object. So yeah, you can't create copies of a node. Like if you have a node in a graph, there's only one instance of it being stored in memory in the graph. Imagine you're like, think of it like this. A node is like a gigabyte, say, and you don't want to have more than one copy of it. So you need to use pointers. You need to use smart pointers. Maybe you use unique pointer with observer raw pointers, or maybe you use shared pointers with weak pointers. Like that's up to you, and that depends on your data structure and depends how you're trying to approach it. We don't have that constraint with the edges. You can have multiple instances of an edge in memory if you need to, though generally we basically are saying that if you have multiple instances of edges for no good reason, then we won't be happy about it. Visin says, so we should only be calling one make shared or make unique. So yeah, generally speaking in this assignment, you're going to end up using unique pointers or shared pointers. You're not really going to end up using both. So you kind of just have to make a call based on your data structure. I'd probably recommend that you choose your data structure and then you try and make sense of what pointer makes the most sense. Don't do it the other way around. Yeah, so that's how you should do it. Yeah, we use smart pointers because if we didn't use smart pointers, there'd be so much copying happening all the time. Like that's why we like pointers, even though, you know, and the other thing is you can't, it's not, there's really long-winded reasons why having a vector of references isn't great and stuff. So like we kind of make out like pointers are evil, right? It's just that pointers aren't always, there are sometimes better solutions to pointers. Sometimes they're not, and that's really as simple as it is. The only thing I would say here, yeah, I mean, all of this makes sense. It's all pretty similar to the previous assignment. I'm sorry, this one's wrong. That's the one thing I did miss. That's just the wrong, but you all know how to clone things by now. Sorry about that. I'll fix that up, but that's no big deal. Marking criteria is exactly the same as the previous one. We have Clang format things, we have best practice things, tests, correctness. Your tests are probably going to be very similar to assignment 2. You'll probably have like 30, 10, 50, I don't know, however many things you want, a bunch of things you want to test, like different properties. Generally speaking, you know, you've got all these different functions and things you can do. Tests should be the easiest part. My personal recommendation to you as your friend is probably to write a little bit of the assignment until you get it, and then go write all your tests. It'll make your life a lot easier. Yeah. So I wouldn't expect you all to start writing tests for templated types if you know, I mean, you could actually. It's actually not that hard. But I get that you want to get your hands dirty sometimes. You know, I get that. Though, make sure you don't write tests till the end. You'll just write better tests and you'll get better marks if you write your tests at the start. So that's probably one recommendation I have. If you do have any other questions about it, then the best place to look is, we have a pinned post, assignment 3 spec questions. Nathaniel has been on this like, I don't know, some expression that describes like something that's really intense and good. Nathaniel's just been smashing, getting, look, 21 hours ago, 4 hours ago, a day ago. I mean, you get the point. Nathaniel's just been on top of this. Pretty much every single time I've gone to answer one of your questions, Nathaniel has answered it for you already. So big thank you to Nathaniel for that. And yeah, if you do have questions about the spec, then just post here. Again, this is not us debugging your code. This is you clarifying stuff. It's also a great spot if you have questions to kind of skim through this. Maybe there'll be a little bit of help here in your understanding that you didn't realize you needed. So yeah, that's where to go for that. And yeah, I think that's about it. Honestly, it's like I like this assignment because it's in some ways the easiest one to start because of assignment 2. Like you kind of get it. You know, you got a class, you got functions, you just got to do it. You can do the iterator later. You can finish this whole assignment without the iterator. Oh, and just in advance, someone's going to ask this question at some point. How many marks will I lose if I don't do the iterator? I don't know. Like we don't really plan for that. But if you want a number, like if your iterator just flat out doesn't work, maybe a quarter of these performance marks, I would guess. It depends on the tests we write. Like that's it. Like so you probably can't get about 15% of the assignment or overall marks if you don't do the iterator. So, you know, I would say, you know, do that last or just don't stress about that. There's so many easy places to start with this. Like you can just make a graph and then you can just add the node and remove the node and yeah, it's just such an easy thing to start. Erase it, print it out. Construct it and print it out. Start with that. Go do those 2 things, fill in the rest of the gaps. You'll get enough confidence to do the iterator and you'll just, you know, spend the time on it. You'll be okay. I have faith in you all. Insert edge, insert node. Anyway, it's 7:59, so let's stop here. Thank you again for coming along and listening and all of that. And if you have other stuff, post on the forum. Otherwise, I'll see you all next week and I'll send you an update on Friday. Thanks for being such a bright, smart bunch of students. And yeah, I guess the last point, Nathaniel's encouraged me to remind you not to get caught up on complexity. When tutors mark this, we're not going to like be looking at complexity like really deeply. Like we'll probably ask them to have a glance at it, but they're not going to be like analyzing it in detail. So in a lot of ways, this is mainly just a guideline for you. All I'd say is like, you don't have to treat it like something terrible will happen if you don't do it. It's a general guideline, and if you violate a lot of them, there's probably going to be some penalty, but generally don't get too caught up on it. Just focus on implementing it. But yeah, anyway, have a great night, everyone. And I'll see you next week. Thanks.